So welcome back, Level 3 physicists, continuing on with the Level 3 external on electrical systems. Today we're looking at capacitance. Okay, so what is capacitance, or what are capacitors? Okay, capacitors basically store energy in a circuit by storing charge. Okay, so basically, in its simplest form, in which we look at least in Level 3 physics, it is made up of two separate parallel plates, as you can see in Figure 1. Okay, so in between the plates, we have an either air, vacuum, or a non-conductive material we call the dielectric. Okay, and there's many types of capacitors, and in this topic we'll study only essentially the parallel plate capacitor. Okay, so we define capacitance, capital C, as the charge Q per unit voltage, which the capacitor is capable of maintaining. Okay, and this is known as the farad. Okay, so capacitance, the symbol is capital C, the units are farad, or charge per volt. Charge, of course, the symbol is Q, and the units are the coulombs. And voltage, the symbol is capital V, and the units are the volts, which is V as well. And in a circuit, capacitance can be arranged in several ways. Okay, so one way would be parallel. Okay, in a circuit, as you can see in the diagram there. Okay, and just like you can connect resistors in parallel, so you can connect capacitors, but the difference is that the sum of the two capacitors equals the total capacitance in a parallel circuit. When you have capacitors in parallel, which is kind of the opposite of the equation for resistors. And in series, as you can again see in the diagram, again similar to as you would with resistors, but this time 1 over the total capacitance equals 1 over C1 plus 1 over C2, etc., etc., which again is kind of the opposite of the formula you would have used for resistance. Okay, so you've got to be careful in using the correct equation when you're doing capacitance in series or parallel. Okay, so as discussed earlier, dielectric materials. Okay, so as we've said, basically a simple parallel capacitor consists of two conductors or parallel electrical plates separated by this space in the middle which doesn't conduct. And basically the idea is to get your capacitors as small as possible. Okay, so a large capacity, large charge on those two plates with a small space between them, because space is at a premium. Okay, so capacitors are used for a range of things, from voltage smoothing for AC/DC circuits, timing devices, because obviously you can time the time it takes for the electromagnetic force to be applied to move the currents or move the charge on the other side of the plates. Okay, and remember, of course, that the net charge of the capacitor is 0 because the charges will equal the same on both sides. So looking at these dielectric materials, you basically want a large capacity with the smallest space as possible. Okay, so in order to increase the capacity of a capacitor, okay, for its ability to store charge, there's two ways you can increase the capacitance. You can either increase the area of which charge is stored. Okay, it's because charge gets to spread out more, which they quite enjoy if you're anthropomorphic, or you can decrease the distance between the plates. Okay, this increases the attraction of the opposite plates each other, and therefore it's easier for the electromagnetic force to then be applied across a smaller distance in terms of the electric field. If it was a larger distance. Okay, so it's easier to the charges to basically be pushed off the other corresponding plate. And this is all down to the permittivity of the material inside the capacitor. Okay, so this charge on the plates can leak in airs and vacuums. So we have this material in the middle called a dielectric, which you put between the parallel plates, and this reduces the arcing. Okay, you don't want that. You don't want electrons to jump across. And also decreases the electrical force, increasing the capacity of the capacitor. Okay, so basically what permittivity is that it is the basically the ability of a electric force to move through, or for that charge to move through that particular medium. Okay, and the way it works is it's basically relative permittivity. Okay, so relative permittivity is the permittivity of the substance divided by the permittivity of free space or a vacuum, which will be given in the exam, and that'll be 8.85 times 10 to the negative 12 farads per meter squared. And there's some examples there of some relative permittivity. So basically, the higher the number, the harder it is for that charge to move between that space. Okay, and then we can apply that to the capacitance for a parallel plate capacitor by adjusting the earlier equation. So the capacitance of this plate, double plate capacitor, will be E0, the permittivity of free space, times its relative value from the previous slide, times the area of the plates, divided by the distance between the plates. Okay, so capacitance increases with area, or increases with a smaller distance. Okay, so capacitance, the symbol of course is going to be C, and the units are going to be farads. Relative permittivity, the symbol will be the epsilon, R, and that's going to have no units because it's relative. The area will be, of course, capital A, and it's in meters squared, and the distance will be lowercase d, and the units, of course, are meters. So how does this all work in terms of the dielectric? Well, what the dielectric does is it basically reduces the strength of the electric field by that ratio. Okay, of E naught divided by, or epsilon naught divided by epsilon. Okay, so the chemistry here, so the molecules in the dielectric basically become polarized, bits of it become positive, bits of it become negative in response to this new electric field, and that creates an opposite electric field which pushes against the original electric field and cancels out some of the original field. Therefore, the electric field decreases, and because charge equals the capacitance times the voltage, and of course from level 2, voltage equals the electrical field times distance, then the capacitance will be the charge divided by the electrical field times distance. So therefore, small electric field, the larger the capacitance, because it's an inverse relationship. So in terms of the energy being stored in the capacitor, okay, you basically see that for the work done by a cell is given by the charge times the voltage. And that's all well and good when voltage and charge are constant, okay? But if they're not constant, then if you plot for the capacitor voltage against charge, the area under the graph will be the work done. And because you need energy to do work, therefore the area, being a triangle, will be equal to half base times height. So therefore the work, which is basically the same as the energy required to do that work, equals half QV. And this is essentially the energy stored in the capacitor. Okay, so why isn't it QV? Well, that's because when the electrical energy is being passed from the battery to the capacitor, some is lost in heat, sound, and internal resistance in the wires, for example. And then we have the discharging of RC, so resistor and capacitor circuits. So when they're fully charged, you will see that the switch being moved to point B in the diagram, that means the charge begins to be released from the capacitor. The plus on the top plate then travels clockwise along through the wire and then through the resistor. We can then apply Kirchhoff's law, and we also know that current is change in charge over change in time, and that will equal negative Q divided by the resistor times the capacitance, or resistance times the capacitance. And the reason why it's negative, it shows that the change in charge is always negative during discharge. That's what that actually means. And this is also related to something called a time constant. Okay, so we can write the results from that discharge in the previous slide as current equals change in charge over change in time, which is negative Q over tau. Now, tau is the time constant, and that will be equal to the resistance of the resistance in the circuit times the capacitance in the circuit, the capacitor value. Okay, and it's basically this Torr value, the time constant, is the time it takes for the voltage to go down from its maximum, okay, or the initial, by 37%, okay, or by 63%, sorry, to get basically 37% of the original value, and therefore it's going to be equal to the R resistance in the circuit times the capacitance in the circuit. And finally, that's just a summary of the discharge charge curves. So you'll basically see that for a capacitor, the voltage when it's charging over time is the only one that kind of goes like that, and all the rest, the voltage time and current time graphs, are all the K curves like that. Okay, and the area under the curve of the current time graphs represents the total charge held by the capacitor.